We had a number of different kinds of forces, tension and the normal force. The normal force is in what direction? Is what? It's perpendicular to the surface, so it's always perpendicular to the surface. So for example, if I'm standing on the ground here, it's pointing straight up, all right? If my surface is an incline like this, then it's going to still be perpendicular to the surface. You'll follow me on that? All right, so that's the normal force. We did friction, which I'm going to revisit for just a bit today, and weight, which, remember, what was the difference between mass and weight? Mass is a measure of what? Inertia, right? And the amount of matter, but we characterize that by inertia. And weight is the measure of rhymes with horse? Force, right. So weight is a measure of a force. They're closely related, but they're still different. Within friction, we had two different types of friction. We had static and kinetic friction. And we said that one of these was generally larger than the other. Which one was bigger? Static or kinetic? Right, so static friction is bigger than kinetic friction. That's why when you're trying to push a box across the floor, a heavy piece of furniture, it's more difficult to get it started. But then once you get it started, it's a lot easier to keep it moving. Have you ever pushed a big heavy piece of furniture? File cabinet or whatever? That's because the static friction, you have to overcome the static friction, and then the kinetic friction kicks in, and it's smaller value, so it's easier to push. Did y'all do the thing, stop at the stop sign yesterday? Did you feel the little lurch forward? Yeah, it's pretty cool, huh? And did you tell your friend that was sitting in the passenger seat? Static and kinetic friction. Static's bigger. Is that what you said? Did you say to your friend? Is that the rule? No cop, no stop? No, that's not the rule. Okay. There's another kind of interesting thing that I wanted to point out to you, and those are ABS systems, or anti-lock braking systems, ABS. And ABS basically, when you're stopping, the ABS, anti-lock braking system, you don't need to know what it means, but it's on your car, the anti-lock braking system. The ABS keeps your brakes from locking up. Meaning that it keeps your wheel rolling continuously, but it slows down, but it continues rolling. This is sort of the newfangled way of doing what in old cars? When you wanted to stop, what would you do? What did you do, the brakes? No, not the emergency brake. No. No, you would pump the brakes, right? Y'all ever have an old car and you pump the brakes? A car that doesn't have ABS, you want to pump the brakes, especially if you're on a wet road, so that the wheel doesn't stop turning immediately, but instead it slows down gradually. And so you pump the brakes. And so the ABS, actually, it does that for you. It pumps the brakes. So there are these little actuators on the brake pad, and instead of just closing the brake pad down on the rotor, it closes it, lets off, closes, lets off, closes, lets off very quickly, so that your wheel never actually stops turning. Why wouldn't you want your wheel to stop turning? That just sounds like the craziest thing, huh? What kind of friction is it between your wheel and the road? So let's say this is the road, and this is your wheel. It's an oval wheel. I'm trying to develop a patent for an oval-shaped car wheel. So that was a joke. Right? That would be very bumpy. All right, so our wheel is turning in this direction. There is a contact between the wheel and the tire and the surface of the road at that point. What type of friction applies there? Is it kinetic friction or static friction? This is when your car's moving, okay? The tire's rolling. What kind of friction? Kinetic? It's static friction, right. So if you imagine that you have this wheel and it's rolling along, notice that the surface of the wheel, imagine this wheel in your mind, okay? The surface of the wheel is never moving with relation to the road. But instead, if the wheel doesn't turn, it slides along the road. And what type of friction is that? If it's sliding across the road, that's kinetic friction. Kinetic. If the wheel isn't turning, kinetic friction is in play. If the wheel is turning, static friction is what's holding your car on the road. If the wheel is turning, static. Because as it turns, the surface of the tire and the surface of the road, they're stationary with respect to one another. Now the wheel's turning, right? But the actual surface of the tire and the surface of the road are stationary with respect to one another. And it's only when the wheel doesn't turn that it slides along the road. Now, why wouldn't you want your wheel to lock up then? What's that, Fazal? Okay, it won't stop. When you want to stop, right? But remember the ABS, when you want to stop, instead of just stopping your wheel right away, it does it gradually so that your wheel keeps turning. What? No, not your car can flip. Oh, I guess that could happen. Let me write it up here. Make sure it's clear. All right. So first of all, when the wheel is turning, or when the tire is turning, static friction. Remember that's a script F with a lowercase s. It's between the road and tire. Right? When the tire stops turning, or when the tire skids across the road, kinetic friction is between the road and tire. Right? And ABS prevents this from happening because it doesn't allow your wheel to lock up. It allows it just to keep turning. Why wouldn't you want your wheel to stop turning? What about this statement? When the tire skids, the kinetic friction is between the road and tire. What do we know about the difference between kinetic and static friction? Do you want a lot of friction between your tire and road or not very much friction? You want a lot of friction, right? As much as you can get because that's what keeps you on the road. If you don't have much friction, like in wet conditions or icy conditions, you're going to slide all over the road, right? So what this does is it prevents the kinetic friction from kicking in. This ABS system, the anti-lock braking system, prevents your kinetic friction from taking place, and the kinetic friction is a lower force, a smaller force than the static friction. Y'all with me on this? Yeah. That's kind of cool, right? So today, instead of coming to a gradual stop at the stop sign on your way out, I want you to get out here on Maidwood, and between Beauregard and, like the last 100 feet, I want you to get up to about 70 miles an hour, and then slam on your brakes and try to make it skid. Yeah. And then you can tell your friend, did you see that the tires didn't lock up and that we stopped just fine? Yeah. All right. When I was a kid, we had this old truck. We had a 64 Ford, and that truck didn't have any brakes at all. And it was just sort of like an around the house kind of truck that we did work around the house. And we'd drive down the road to get a soda or whatever, and then we'd come back. But we would it was standard transmission, so we would gear it down as slow as we could whenever we wanted to stop, and then we'd do what? No, we wouldn't drag our feet. Like a 2,000-pound truck. No, we'd find a tree and we'd run into it. Crash. Every time we wanted to stop. No brakes at all. Certainly no ABS. All right. All right, let's do some more of this concept test. We had done part of it, and I want to do some more here. You have to help me out here. I think we did the fly problem last, right? The fly on the truck. This one. And it accelerates backwards. All right, excuse me. It accelerates. Yeah, the fly smashes into it, and in the instant, it accelerates backwards, and then after that, the truck moves back at a constant velocity. Okay? Go with me? And y'all are wild on that. All right, let's say that we have a stone and a feather, and they're falling within a tube here. And I want to know which of these statements about the force of gravity. And remember, what type of force did we call that? The force due to gravity? We called that the what type? I didn't hear you. What? It's the weight. Thank you, Tori. It's the weight. Uh, so what can you say about the weight acting on a stone and a feather? This is meant to be obvious. Stop at 55. Let's see. B is the correct answer. The stone has more mass. It also has a greater force acting upon it. Remember how we calculated that force? It was from the law of acceleration. The law of acceleration says that A equals F over M. And we said that that acceleration had a particular value for gravity. What is that equal to? It's equal to 10. And so I can calculate the force due to weight is equal to M times the acceleration due to gravity. The acceleration due to gravity. And so that's equal to M times that acceleration, which is in meters per second squared. All right? So because the stone has a larger mass, it also has a larger weight. That's obvious, right? Yeah, somewhat. Well, let's try this next one. What can you say about the acceleration of gravity acting on the stone and the feather? Now these are falling within a vacuum. So how are they accelerating in comparison to one another? In a vacuum means there's no air or whatever. I'll stop at 40 seconds. 5 more seconds. Okay, D is the correct answer. We just said this, right, that the weight, Fw, is equal to M times G. So if I have a mass of 70 kilograms, for example, then I could find my weight would be 70 kilograms, which is sort of the mass of a typical person, times 10 meters per second squared, and then I would get the weight, which would be 700 newtons. And that's the weight of a typical person. But if I had a mass of 1 kilogram, it would have a weight of 10 newtons. All right? So the acceleration due to gravity where we find this weight is the same for all objects. Can I have a sheet of paper? Like a scrap sheet of paper? So if I have two objects, so basically what I've just said is that if you release something within the gravitational field of the Earth, that they're going to fall at the same rate. Do you think that's true? Like if I drop this weight and I drop this sheet of paper, which one's going to hit first? Let's try it. Y'all ready? That was kind of close, right? I think it might have been the same. But what if I did something where like I crumpled this paper up? Then what would happen, you think? You really think they'd both fall at the same time? Let's try it, okay? I want to see what you think. So if you think, once y'all click in, there is no right or wrong answer here, but if you think that they're both going to hit at the same time, then click in A. Or if you think the weight hits first, click in B. All right? So if they hit at the same time, now we'll make it a right or wrong answer. So put in what you think, and then whatever happens, we'll give that to be the right answer. If you think they're going to hit at the same time, click A. If you think the weight, the heavier one, is going to hit first, click B. Just a few more seconds. Stop at 38. see what y'all think. Okay. All right, so y'all ready? Ashley, you're sort of the judge, okay? Are you ready? What happened? Oh, come on, it wasn't close. Like the previous one was close. No, that's wrong. That's wrong. No, they both fall at the same rate. It is close. I agree. And you might be a little bit right, but if you did this many times over, I'll do it again. Can you? Oh, really? They're going to hit at the same time, okay? You ready? They hit at the same time. All right? So that's because that acceleration due to gravity is the same. Now, what did I change about the paper? I changed the surface area, which changed the what? The air resistance, yeah. So I actually have this force that's pushing the paper back up when it's a whole sheet of paper that causes it to slow or to fall more slowly than it would normally. Natalia? Oh yeah, A was supposed to be the right answer. Did I mark B? Oh goodness, you all put B. I thought you were all just really sharp. You are sharp. You're very smart. Okay, so A is the right answer. All right. So the acceleration due to gravity is the same always. But it just happens, like for example, if you're dropping a big sheet of paper, you have that air resistance that causes it. Or if it's like a feather in this case. That's another little thing that you can do to impress your friends. You can take something heavy and a sheet of paper and ask them which is going to hit first. And then you can like put money on it and all that jazz. And then right before you drop it, you crumple up the paper. And then you win the bet. Okay? I don't condone gambling, but all right. Okay, this is about normal force. I'm going to skip this one. We're going to move up to this one. Say that you're in an elevator, and this is a block of mass m. So consider that you're a block of mass m, and you're in an elevator that's going up, right? It's traveling upward, and it's actually accelerating upward. What is the relationship between the force due to gravity and the normal force on the block? Now, normally, like if I'm just sitting here, normally, ha ha ha. You get it? We're talking about the normal force. Normally, if I'm just sitting here, I'm 700 newtons roughly, okay? What is the normal force pushing back up on me? 700 newtons. So what happens here? If I'm in an elevator that's rushing up, accelerating upward, what happens to the normal force? Is it bigger, equal to the weight, less than the weight? Is the normal force 0, or does it depend on the size of the elevator? All right, I'll stop at 1:15, let's say. 1:15, 5 more seconds. Let me show you something. I have this elevator right here, this person inside of it, and I have two forces acting on it. I have the force weight of the person, and then I have the normal force. How would I write the net force on that person? Remember, what was the net force? It was something. The sum of the forces. Thank you, Sydney. It's going to be the sum of the forces, which in this case would be Fn, which is in the positive direction, minus Fw. They're opposing one another, so I have to take the difference between them. Remember, like me and my brothers pushing on the car, right? You take the difference in those two. And we said that that net force, which is what we've done here, by Newton's second law, which is the law of acceleration, is equal to mass times acceleration. All right, so what we're saying here is that the normal force minus the force weight is equal to the mass times the acceleration. All right, so now I want to know how does the normal force compare to the weight? Why don't y'all try this one more time? I'll give you a hint. It is either A or B. Those were the two most popular answers, and one of those is correct. But which is it? All right, I'll stop at 32. 32. Okay, that's a little bit better. A is the right answer. You can see this mathematically. If you look at it, then I'll explain sort of how you experience it. If this is a non-zero number, which it is, say it's 5 or whatever, then I find that the normal force is equal to the weight plus that value 5 or whatever it is. All right? And then the normal force has to be larger than the weight. Now, how does this feel in an elevator? When you start going up, what do you feel? You sort of feel like you're being pushed down into it, right? In a similar, I mean, that's a very subtle effect. But have y'all ever gone to like a carnival or a fair where they have that ride that spins you around? That's a similar thing where the wall, is the normal force, as you spin around, the wall is pushing on you and the normal force increases. And it's like your face just does like this. All right, you have this effect on your body that you can visibly, or like actually feel. All right. Imagine this one. I have two identical blocks, one on a flat surface and one on an incline. For which is the normal force greater, A or B? Remember, the normal force is that perpendicular force. If I push down on a surface, it pushes back up on me. And guys, I'm going to put these all online, so you're welcome to take notes on them, but they'll go online when we're done with them. All right, I'll stop at 55. 55. Let me show you something. Look, you remember that our static friction, we said that our static friction, oh, did we say this actually? I'm not sure that we did. We said that the static friction was proportional to what? To some value. I remember some force. What is the friction proportional to? The normal force. Thank you, Shauna, right? Yeah, the static friction. Did we use that mu, that little U-looking character? I don't think we did. Oh, okay. The static friction is proportional to the normal force. That means that if the normal force goes up, the static friction goes up. And we sort of said this, you know this experientially, that if I have an object and I push on it, it's going to have more friction, right? It's going to be more difficult to push. And to make it easier to push, I pull up on it like this, and then it's easier to push. Because by pulling up, I've decreased the normal force, and that decreases the friction. Well, let's imagine this. I have this weight. There is a certain amount of static friction between the weight and the surface of the table, right? Now, I can decrease, or I can increase that amount of static friction just by pushing down on the weight. And that increases the normal force, and then that increases the static friction. But notice what happens, what's going to happen if I lift it up? It's going to eventually slide, right? So what have I done to the static friction? It's no longer big enough to hold it in place. What have I done to it? Increased or decreased? Decreased it. And how have I decreased it? By pulling up the incline. Remember, the static friction is proportional to this normal force. So let's try this problem again. It is either A or B. Oh, did I just say that out loud? It is either A, B, or C. Yeah, it could be any of them. I'm sorry. All right, I'm going to take this away. Stop at 28. Excellent. Good job. That is perfect. I mean, I'm going to give y'all a joke. You want to hear a joke? All right. This is kind of a, if you're easily offended, just plug up your ears, okay? Y'all ready? Because it's kind of an offensive joke. You ready? What is the worst thing about living on O Street? And this is what, like, I mean, give it some joke etiquette. This is where you say, I don't know what. You have to walk a whole block to pee. You have to walk a whole block to pee. Like O Street, P Street, the whole block to pee. All right. Let's see what we got. Okay, let's pause there. So we'll come back to this. What is this? 4.13a. As we're going through this chapter, we'll come back to these periodically. We just want a little break from stuff. By the way, when we're done with this chapter, like if you're in my Physics 101 course, which is a 2-semester course, after this chapter, it's like the amount of material that we would have covered in, I don't know, 2/3 of that course. So we're going over a lot of different stuff, so we're sort of glossing over a lot of things as well. So there are a lot of details that we aren't going into, but that's okay, right? All right, let's look at torques. Torques, soon we're going to get into muscles and the body and how torques are applied, but first we just want to identify what torques are. You probably know what a torque is. A torque, you can think of it as a force that causes rotational motion, or akin to a force. Don't write that down. Hold on. A force causes linear motion, acceleration in particular. All right, so if I put a force on an object, it's going to cause it to move. A torque, on the other hand, which is very similar, causes rotational motion. All right, so if I have this and I apply a torque to it, that means, let's say I have it rotating about this axis right here, all right, and then I apply a torque to it. I'm going to put a force right here. I'm going to cause it to move in a rotational direction, in a circle, okay? So torques cause rotational motion. Where have you heard the word torque before? On a motorcycle? On a car? Okay. Like a torque wrench. That was the answer I was looking for. Like a torque wrench, okay? And a torque wrench, you know, you have this big long bar and you use it to turn things, okay? And you can actually measure what is the torque that you're giving. All right? We're going to define torque. We're going to use the Greek letter tau. It looks like a T, sort of, with a squiggly line on the top. The torque is equal to the force times the length of the moment arm. And in particular, this force is perpendicular. So I'm going to put a little upside down T. That just means that the force is perpendicular to the moment arm. This is called the length of the moment arm. And this is the perpendicular force. So let's say that I have an object here. It's rotating about this axis. I apply a force here. Let's say that the force is, I don't know, 2 newtons. And this distance we'll say is 3 meters, then the torque is equal to that force, which is perpendicular, times R, which is 3 meters here. So it's going to be 2 newtons times 3 meters, which is equal to 6 Newton meters. And that gives me the units then of torque, which are the units of force times the units of meters. If you've ever used a torque wrench, sometimes they'll have Newton meters on them. Other times they'll have what units on them? More common, actually. On a torque wrench? Foot-pounds, right, because the foot is the British measurement for distance, and pounds is the British measurement for force. So Newton meters or foot-pounds are the units for torque. Now, imagine that instead of having a force that is like this, that you have a force of 2 newtons that is like that. Do you think that that would give you a larger torque, a smaller torque, or the same torque? Let's try clicking this in. Would that give you a larger torque, a smaller torque, or would it be the same torque? Larger, smaller, or the same? If I pull like that. That is, instead of applying my force perpendicular, I'm instead applying my force at an angle like this. But I'm still applying a force of 2 newtons. Does it give me A, a larger torque, B, a smaller torque, or C, the same torque, as if I applied it perpendicularly? All right, I'll stop at 45. Excellent. B is the right answer. We're not going to get into the mathematics of it, but because we need trigonometry to do so. But if you imagine this force that I've now, this 2 Newton force that is now not perpendicular, that force is actually broken down into pieces. One piece of it goes in that direction, and one piece of it goes in that direction. So the perpendicular part of that isn't exactly 2 newtons. It's something less than 2 newtons. And the perpendicular force is the force that causes torque. You can imagine that, because say I have this thing and it's allowed to rotate like this. What if I push in this direction? What kind of rotation is that going to cause? If I push in this direction? No torque at all, right? Because that's not a perpendicular force. That's a parallel force. I have to apply my force perpendicular. Right? That would be like, trying to open a door. Can y'all see me? And I push like this. I'm never going to get the door open or closed, right? Because I'm applying the force in the wrong direction. I know y'all couldn't see that. It was great, though, okay? It was like the best. If you missed it, sorry. Okay? All right. So next time you go out, you can tell your friends, hey, let's try this new way of opening the door. And instead of applying a perpendicular force, I'm going to apply a parallel force and see if I can get it open. And then they'll just think you're an idiot. All right, let's do a problem. Now, one more thing. When an object is not moving, or when an object is not rotating, and there are some problems like this in your book where they do static equilibrium problems. We say that it's in equilibrium. The net torque equals, what do you think? Is 0, right. This is just like the forces. Remember we said that like if I'm standing around or you're sitting or whatever, or that you have a lot of forces acting on you, but you're not moving, right? And that's because the net force acting on you is 0, because you have some forces that are pushing up, some forces that are pushing down, you have forces pushing side to side, but those all add up to equal 0 when you add up the sum of all those forces, the vector sum. And the same is true for torques. This can be a little confusing, but let's just work through this. Let's show you that if I have this object, let's say that it is 2 meters long, it is rotating about this, so I usually use this little caret symbol to represent the pivot point, or sometimes in your book they use a triangle to represent the pivot point. I like to think of it as a seesaw. Like on a seesaw, that's where you pivot at the triangle. Let's say that I have a force here equal, I'll call this F1, equal to 2 newtons. And then over here, I have a force in this direction, which I'll call F2, equal to 4 newtons. Now, is that object going to move or not? We want to see what is the net torque. Now, I can calculate the magnitudes, or the values for these torques. Torque 1 is going to equal to F1 times 2 meters. Right, which is going to equal 2 times 2, which is 4 newton meters. Right, this torque is in the clockwise direction. The reason it's in the clockwise direction, imagine I have this object, it can rotate either that direction or that direction. If I have a force that's pulling up, like F1, that causes this to move in the clockwise direction. You'll follow me on that? On the other hand, this force causes what kind of torque? Counterclockwise. Because if I pull down on it, that causes counterclockwise torque. Go with me on that? The students often have difficulty with that. So if you have a problem, and you will, and there are some problems in the book like this too, and you actually had a problem on your quiz. Remember, didn't you have a problem where it asked, was it a counterclockwise or clockwise torque? Yeah, the guy, I think it was the guy bent over. Yeah, we'll talk about that soon. Imagine that you hold your lever arm. I usually use my pencil or pen or whatever, and hold it at the pivot point, and then ask yourself, well, if I pull up, it's going to cause that clockwise motion. Or if I pull down, that's counterclockwise motion. We'll get some more practice with that. We'll do some clicker questions next time. Okay, so torque 2 then is F2 times 1 meter, which is 4 newtons times 1 meter. So that's 4 newton meters. And we've already said this is counterclockwise. All right. Now these are equal but opposite torques. So the net torque equals, our convention would actually say torque 2 minus torque 1. Don't worry about that too much. But the idea is here that our net torque is 0. And so this is an equilibrium system. It's in equilibrium. It's not moving. It's not rotating. All right? Let's try one on your own. Yeah, Destiny, right? Oh, I didn't. It was sort of assumed. Is that this force was midway between on the lever arm, and so this distance is 1 meter. That's a good question. Sorry, I didn't label it. All right. Let's work one on your own. So I'm gonna give you a problem, and I'm gonna ask you what is the torque or what is the force required to hold it in equilibrium. So let's say that I have a seesaw. This seesaw has a length of, I don't know, 6 meters. Okay? Has a length of 6 meters. Like good seesaws, it pivots in the middle. So these lengths right here are 3 meters. I have a person of 100 newtons on the end. That's a little bitty person. So I have a person of 100 newtons on the end. Where can I put a person? Well, let's say that I have another person that is 1 meter from the middle. I have a person that's 1 meter from the middle, and I want to know what is the weight of that person. Okay? And give you some options here. Let me think. I'm going to blank it out for just a second. I'll give you all a second to write that down. I'll come up with some options. And go ahead and start trying to figure it out. So you want to balance the torques, right? This is a rotational equilibrium problem. They're balanced. So I know that the torque on the left-hand side, or the counterclockwise torques, have to equal the clockwise torques. I'm going to blank this out for just a second. I'll bring it right back. Okay? And then you can click in when you get the answer. There are your options, 300, 133, or 200. That is, what is the weight of the person right here that will balance the seesaw? If you have kids, you probably know this, sort of, intuitively. From 1 meter from the center. You can talk to one another. It's fine. If you need help, you can ask your friend or your neighbor. I'm going to stop in about 10 seconds. If you don't know, just guess. Stop in 5 seconds at 120. Hey, excellent. That's right. Why did I say if you have kids, how do you know this intuitively? Right, yeah. Yeah, so like if you have like your little 5-year-old girl and she's on the end and she wants you to seesaw with you, you have to sit closer to the middle, right? But let me show you how to work this. I can calculate my clock, or let's see, what type of torques is caused by the 100 Newton person? Is that clockwise or counterclockwise? It's counterclockwise, right? It causes your thing to rotate in this direction. So that's counterclockwise. So my counterclockwise torques is equal to the force perpendicular times the length of the moment arm. That's going to be 100 newtons times 3 meters. So my counterclockwise torque is 300 newton meters. Now I know in order to balance that, I have to have 300 newton meters for my clockwise torques. So my clockwise torques, which are equal to the force perpendicular times r, I know this is going to have to equal 300 newton meters. I know that because this torque was 300 newton meters, and to have equilibrium, those torques have to cancel out. And so that's going to equal my force times 1 meter. Then what times 1 gives 300? But 300. If you wanted to do this more rigorously, you would divide both sides by 1. These ones would cancel, and you would get the answer 300 newtons. See that okay in the back? I'll give y'all just a minute. We're going to look at levers now. And if you remember in the reading, in fact, one of the quiz questions was the different classes of levers. We're also going to look at the different classes of levers in the human body next time. Next time, basically, we're going to be talking about the body, which I know is sort of your bread and butter. And you probably know more about it than I do. But right? Because I'm just reading this book, man. I don't, that's really all I know. Can I go on? All right. Let's look at the classes of levers. There were 3 classes of levers. There's a figure in your book for these. Class 1 looks like this. My effort, that is the force that I apply, is here. My fulcrum is here, and your load is over here. All right, so that's one class of lever. Class 2 levers look like this. Your fulcrum is at the end. That's your pivot point. Your load is right here. And your force is right here. And then class 3. And by the way, these are organized in order of efficiency, or the least amount of force that you'll need to lift a load. For class 3, your fulcrum is here. Your force, or your effort, is right here. And your load is right here. And we see all three classes of levers in the human body. But we're just going to look at them now in this way. All right? We're going to do a little activity where you're going to build these levers. So I'm going to hand you a ruler. And you'll need to work with, let's just try working with the person like right next to you. All right? So if you dislike the person next to you, like these 2 rows, and these 2 rows, you should just get up right now and move to a different seat. Like if you look at the person, if you dislike them, just get up and move, okay? And make a big show out of it, okay? All right, just find somebody, it's fine. All right, I'm going to hand y'all some rulers first. And the first thing I want you to do is just make a class 1 lever. So I'm going to hand you a ruler, and then I'll hand out some masses. 3, 4, 6, 7, 8. Well, that's not a very good lever, is it? These are special college rulers, so they're very expensive, so please don't break them. I'm the math coach at my kid's school. He's not on the math team. He's like 3 years old or whatever. And I always bring pencils, and I always tell them, these are college pencils. And they're like, ooh, college pencils. And now I'm going to hand you some weights. The first thing I want you to do is to make a, I don't know that we're going to have enough weights. Pass them back. You might have to improvise and use something that you have as a weight. This, y'all get rulers? Oh no, yeah, they got the rulers, right. Pass those back. All right, so y'all pair up, okay? And the first thing I want you to do is to make a class 1 lever. So you're just going to have to use something as a fulcrum, like your finger, for example. And I want to see the class 1 lever. So you would have your load down here, and then your force would be here, okay? Y'all pair up, get close to one another. We'll take about 5 minutes or so to do this, 5-10 minutes. So I want to see your class 1 lever, okay? Hey, like the Red Sea over here. Set my people free. Class 1, okay? Oh, nice. That's a good class 1. Now, once you get the class 1, I want you to take it and go whoosh, and whoosh, fly the weight over. Once you get the class 1, I want you to go and do the class 2 and class 3, okay? Huh?
But you want us to, like, put the weight where it's supposed to be?
Yeah, I want you to, yeah. No, you're going to use your finger just like she's doing as the fulcrum.
Okay.
And then put the weight where it's supposed to be. That's the load. And then your other finger will provide the force. That's a class 1. Right. Yeah, I just want you to see it. Put your hands on it, okay? What's up? It doesn't really matter. For class 1, the fulcrum is in between the load and the force. A class 1 is like a seesaw, y'all. That's a good class 1. Y'all do a class 2 as well. Good class 1. Yeah, do class 2 and 3. All 3 of them, yes. I'm looking. It's for you. Oh my goodness. Here, you'll get the real thing. Right. So class one's like a seesaw. So go ahead and do 2 and 3. Really? Okay, wait. Huh? The third one. Well, you're going to have to hold it at the fulcrum. I don't know. What's the problem? That looks good. Yeah. So he's providing the force? Yeah. Okay. Good job. Y'all all done? Okay, just a couple more minutes, y'all. Y'all are all done back here, ladies? All right. If y'all could start, if you're done, go ahead and start passing your rulers and your weights up, your masses. Y'all are done? Your quiz grade? Okay. Why don't you see me afterwards? We'll take a look, okay? No, I like y'all like that. If y'all could. Right. Thank you. Thank you, Valerie. I get my university rulers back, my college rulers. Thank you, Julia. Thanks, DJ. Dejanay, right? Yeah, thank you. Where's my other Dejanay? She's not here, is she? Thank you, Shauna. Shauna, right? Daphne? Oh, no, Tiffany. I'm sorry. You're Tiffany. Thank you, Julia. I overheard somebody when they were talking about these. I think it was you, Fazal. Was it you? Talking about how you remember these levers? Can you share that with us? Tell me. Oh, is it? Okay. Okay, class 1 or like a scissors? Okay, yeah, so your force would be like your fingers at this end of the scissors, and this is the hinge where the scissors are located, and that's like cutting the paper? Yeah. All right, what's this one? A wheelbarrow, so your wheels are down here, your dirt or whatever, and then what's this one? Okay, this is the end of your tweezers, the hinge. This is where you put your fingers, and this is where you pull out the splinter. Yeah, let's write that down. I like that. Okay, I guess I didn't really read the book. Okay, so let's see. This was scissors. This is a wheelbarrow and tweezers. Whoop. Thank you, Fazal. It's very useful. All right. Let's look now. I'm going to shift gears just a little bit. We'll come back to levers because we'll look at how different parts of the body have different levers. And that's in your book as well, but you can see it there. May I move from here? Got the levers okay? Scissors, wheelbarrow, and tweezers. That's the easy part, yeah. All right, now we're going to look at muscles and bones and just sort of have some, what's the word? Some words to describe them. Some terminology. That's fancy for word. We're going to have some terminology to describe them. There are 3 types of muscles, which I'm sure you all know. I did not know this until my son went into 3rd grade. But there are 3 types of muscles. There are skeletal muscles, and that's what we'll be mostly concerned with. Because skeletal muscles do what? They attach to the bones. They move your bones, right? They make big external motions, right? We also have, so these connect to the skeleton. This is in your book. and they cause large external motion. All right. Second type of muscle is the cardiac muscle. That, of course, is associated with what? The heart, right? I guess there's just one cardiac muscle. Is that correct? It is the heart. You think they just say heart? And the third type is the smooth. This was one of your questions from your quiz, actually. What was the other type that wasn't a type on the quiz that I listed? A digestive, yeah. So there is no such thing as a digestive muscle. That's the smooth muscles. The smooth muscles are used to move fluids in the body. All right. We're going to look at skeletal muscles exclusively. We might get into the smooth muscles in the next chapter. I'm not sure. Really, I'm just sort of staying like a half step ahead of you as I'm going through the book. So this is my first time to really teach this course in this way. So we may or may not get to the smooth muscles. I'm not sure. Now, the skeletal muscles, a couple of things about those. The way they're attached to the bones. They attach to the bones at two different points. Now, if I imagine your arm, this is my arm. It's like this. My arm bent. Here's my hand. I have 6 fingers. Oh, and then I have this big bicep. Check it out. The muscles in your bicep, they attach at 2 different points. So this is my sketch, but it's attached here and attached here. This point right here is called the origin. Very good. Y'all know this, huh? Because you read the book or you knew it before? It's part of your major, right? Yeah. So this is called the origin. Good. Hopefully this part is really easy for y'all then. This will be on the test too, though, right? So just like it was on the reading quiz. In fact, a lot of the reading quiz was stuff like this, stuff about bones and muscles. So the origin is attached to the end that doesn't move. So it's attached to the bone that doesn't move. And just to set the record straight, I know you can't tell because I have these big clothes and stuff, but my bicep really isn't that big, like in relation to the rest of my arm. If y'all are. And then the other point that it attaches, y'all know this? Gosh, y'all are smart. So this other point is called the insertion point. All right, and this is it's attached to the bone that does move. All right, so the origin and the insertion point. And by the way, we can think of these muscles in much the same way as we thought of a string between 2 people pulling on it. So if I have a certain force that's being exerted here, a certain force, what type of force would that be, by the way, in a muscle? It'd be tension, right? So that force is a tension force. That tension force runs all throughout the muscle. So if I'm applying, 100 newtons of force up here with my bicep, I have 100 newtons of force that are applied all throughout the muscle, from this point all the way down to this point. All right? All right. Now, joints are where 2 or more bones meet. And we're going to look at one type of joint, and then we'll wrap up. The synovial joint. I'm sorry, is it okay if I go down? Y'all good? Okay, the synovial joint. I thought this was really cool, actually. The synovial joint allows for very large movements, like in the arm, for example. I'm going to show you a picture in just a sec. Cartilage covers the ends of the bones. And there's a cavity with synovial fluid for lubrication. Does anybody know what that fluid is made of? I do not. Does anybody know? No, I'll try to find out. I have a picture here. Give me just a moment to write that down. I'll show you the picture. And then keep your clickers out. We're going to do a few more clicker questions before we wrap up. Can I come away from this for just a moment? I'll give y'all just a second longer. What do you do if you're attacked by a group of clowns? What do you do if you're attacked by a group of clowns? Go for the juggler. Okay. Y'all good? You got that? All right. Don't write that down. That wasn't part of the note. Let's see. So here is our synovial joint. So you see you have these two bones that come together. Let me zoom in a little bit. These two bones that come together, and they're covered in this cartilage right here, the ends of the bone. And then you have these synovial cavities that allow this fluid to come between the bones. And that prevents what? What type of force? Friction, right. So it limits the friction and allows the bones not to have too much friction between them. But y'all knew that, right? Okay. All right, good. Let's do some more clicker questions. This is kind of cool, right? All right. We'll just do these for a few more minutes. You might not know this right away, but I think you can reason it out. So I have two objects of certain masses, and there are gravitational forces between them. So for example, me and the Earth is pulling down on me with 700 newtons. And likewise, I'm pulling back up on the Earth. And now I want to know if I had these two objects, like a bowling ball and a ping pong ball, and they're out in space, and they're similarly attracted by gravitational forces, how do those forces compare? Does the bowling ball exert a greater force on the ping pong ball? The ping pong ball exerts a greater force on the bowling ball. The forces are equal. The forces are zero because they cancel out. Are there actually no forces at all? It's just a big scam. It's not a scam. E is not the right answer. Think back to our Newton's laws and think which one would apply here. All right, I'm going to stop at 125. Okay, very good. C is the right answer. Think Newton's which law? Which law is that an application of? Right, the third law. Thank you. Page? Yeah, Page. The third law. It's the third law. For every force, there's going to be an equal and opposite force. And that's true for gravitational forces, too, which should really rattle your brain a little bit. That I can have two objects, just a second, Evan. If I can have two objects that are separated from distance, not touching one another, and yet they exert forces on one another. Evan? The mass has everything to do with it, right. So the bigger your mass is, the larger the force is. I understand what you're saying, but they're both, the bowling ball is going to exert a force on the ping pong ball, but the ping pong ball will exert the same force on the bowling ball. Let me write this. Don't write this down, but I want to show you mathematically what it looks like, okay? But don't write this down, but maybe it'll help you understand. We can calculate this force, and Newton did this. This is called his universal law of gravitation, and he said that that force between these two objects is equal to G times M1 times M2 over the distance between them squared, where the distance between them is R, and this would be M1, for example. This would be M2. Now notice this force has both masses in it, and I can use this formula to calculate the force for both. So here, I would have to calculate the force here. I would consider this force, but I also consider this force. Right? So both masses are concerned when you're calculating the force. So the Earth pulls down on me with 700 newtons. I likewise pull back on the Earth with 700 newtons. If I was a lot bigger, I'd pull back with a larger force. Does that help to answer your question a little bit? It's kind of a mystery, too. They are always equal, right? The forces are always equal. But the forces, if there's more mass involved, the forces are bigger. But they're both bigger by the same amount. The forces are always equal. All right? Newton's third law, Newton's universal law of gravitation, the description of these forces between objects, or, just a second, I forgot what I was going to say. Newton's universal law of gravitation is an application of Newton's third law. They're very similar. Stain, right? What's up? Not necessarily. No, they can move. Right, if you have these forces applied to one another, like a good example, if I jump up, I'm going to fall back down again, right? Because the force due to the Earth, the force due to gravity that's pulling down on me is pulling me back towards the Earth. All right, let's do one more, and then I'll hand back your quizzes. We're going to skip this one. You tie a rope to a tree, and or we might do two or three more, I'm sorry. You tie a rope to a tree, and you pull on the rope with a force of 100 newtons. What is the tension in the rope? It's supposed to be obvious, okay? I'm going to stop at 25. C is the right answer. If I pull with 100 newtons, then I get 100 newtons of tension in the rope. All right, what if I have a tug of war, and I have two guys pulling on either end with 100 newtons? What is my tension in the rope going to be then? I have one guy pulling with 100 newtons, and then I have another guy pulling with 100 newtons on the opposite end. It's tug of war. Right, what's the tension in the rope? Stop at 30 seconds. Hey, good job. Oh, did you not get in? Did I not say it? I said it right. Okay, I'm sorry. Don't worry about it. It's just one question. It's not a big deal. Oh yeah, so this was, we've sort of done this before, that, there's no difference in me and another guy pulling on a rope with 100 newtons and me pulling on a rope with a tree. Right, the tree is still pulling back with 100 newtons. Okay, so if I still have that 100 newtons of tension in the rope. Yeah, DJ. It'd be moving, right? Like in tug of war, whoever pulls harder, they accelerate in that direction. Well, it would be. No, you don't subtract it. I'm not sure, DJ. I'll have to think about that. Okay? I'll think about it. I'm supposed to know, aren't I? Is that what you said? Oh, I thought you said you're supposed to know. You're the teacher. I don't know everything. My bicep's not this big, and no, you can have different forces. Guys, listen, I want to hand back your quizzes, so just hang tight. We can revisit it next time. We have a few more questions in this strain, and we'll revisit it as well. Right now, I'm going to hand back your quizzes, and when you get your quiz, you can go. I'll put the actual quiz online. The answers to the quiz, by the way, I didn't write all of these on your test, but the answers to the quiz are CCACD, CCACD, BDA, and then there were two free response. One that was 10 newtons and 3, 2, 1. 3, 2, 1. All right. So I'm going to call out your name, and you just come get it, and then you can go. Julia, they're in alphabetical order. So if your name starts in A through D, please come on up. That's Ashley. Are you at Otama? Kayla. If your name starts in A through D, just come on up. You can bring your stuff, and y'all can go. Kayla. Jessica. Chris. A through D, come on up. A through D. That's Janae, Valerie, Casey, Jenna, Tori, Taylor. Okay, just a second. Chris, Janae, Janae, Casey. Yeah, you're Janae. Jenna, Tori, great job. Taylor, Dajanelle, it's not here, I don't think. All right, Dajane, Kaylee, you're Kaylee? Great. Destiny, now FGHI, Destiny, Talia, Hannah, Brianna, Daphne, Shauna, Fazal. Oh, good job, Fazal. All right, DJ, Shannon, JKLMNO, Bryce, Evan, Jesse, Paige, DJ. Where's DJ? Oh, there she is. Shannon, Sydney, Bryce. Right. No, you're Evan. You're Bryce. I'm sorry. Y'all stood next to one another on the first day, and I get y'all messed up. Jesse, Paige, Cheyenne. Good job. Reagan's not here. Dejanay. Everybody else. Elise, Kiosha, Dejanay. Elise, Kiosha, Austin, Alex. No, Alexandra Simmons. Okay. Najane. You're Najane, right? No, you're Alana. Najane, I'm sorry. Chelsea. Tiffany. Alana. Josh. You do go by Josh, right? Okay. Alex Tucker. Kylie. And Dane and Macy. All right. Do you want to look at your grades, right?